Hi, this is Professor Fernandez, and this is video 1C in lesson 19. The C here is because we've done two videos before this, video 19.1a, 19.1b, and they've all been on the same topic, u-substitution for integrals. And that's the same topic of this video. So I'm going to wrap up this series of videos on u-substitution by looking through this example, working through it 5.24 from Calculus Simplified. So this is the last of those videos on u-substitution, and that's because I'm increasing the difficulty level as we go through each video. So I only have one example to do here. That'll take us the whole time because there's something very special about this example that I want to point out, and which actually makes it a little harder than the other ones I've done. All that being said, right, I do recommend you take a look at videos 19.1a and 19.1b to get more familiar with the simpler u-substitution examples and some rules of thumb for how to use u-substitution and choose your u. So take a look at those videos. I discussed that in there. Okay, so I'm going to review some of that right here as we start this example. So what are we going to do to try to solve this integral? Well, first of all, how would you know to use u-substitution? The answer is you can try some simpler techniques, and they're just not going to work, right? So simpler techniques than u-substitution are what are called integration by tables. Basically, there's some standard integrals that we know, like the integral version of the power rule, right? That the integral of x to the n is, you add 1, you divide by the result, so long as n is not equal to -1. But this is not that type of integrand. There's also no other, simple integral result that we know of that helps us here. So integration by u-substitution is the first technique you try if none of those simpler ways work out. Great. So then what do I do there? So remember the guiding principle that I gave in those earlier videos was to find the composite function in the integrand. Here it is. And then try the inner function of that composite function as your u. So we are going to try 1 plus x squared here as the u. Most of the time this will work, won't work all the time, especially in some of the really hard integration by u-substitution problems, but should work most of the time. Okay, so if I find then the differential here of u, that's du, it's just the derivative of 1 plus x squared, 2x times dx, great. And then now the next step in u-substitution is to use these two things and re-express the entire integral in terms of u. So how would I do that? Well, let's do the easy part first, right? The easy part is I know 1 plus x squared is u. Here's a 1 plus x squared. So I get the square root of u. Great. And I'm going to leave in here x to the 5th dx. This is, again, the math telling you that you're not done yet, right? This integral now has two variables, but you want it to have only one variable. So we want to continue eliminating what's left of the x's, which is x to the 5th dx. Here is where the greater difficulty level of this problem comes up, because in the previous examples we've done, what's been here is maybe x dx, and we've said, oh, x dx, that's 1/2 du. Great, and then we just replace this by, square root of u du. But that's not what's happening here, so I'm just going to erase all of this. There we go. What's happening here is that we have x to the 5th dx, and the only other thing we have to substitute here seems to be 2x dx. So how can we possibly get that to work out? Okay, well, here's the thing, right? Let's substitute what we can. So what do I mean by that? Well, x to the 5th is x to the 4th times x times square root of u dx. Aha, so I have conjured up an x dx, right? This is, again, why this is a more difficult problem. You wouldn't necessarily know to do that, but now that you've watched this video, you have some sense of, you might try this in a similar problem in the future. So I am going to go back here and isolate x dx, dividing by 2, that's x dx. And I can go back and then express this as x to the 4th times square root of u times d, 1/2 du. Great. So I have replaced x dx here by 1/2 du. All right, that got me a little further along. It removed 1 power of x. Now I still have, I have x to the 4th, but I still have the x's. So what do I do now? Well, at this point, I have used this part of my u-substitution, and I also used that, and I'm down here. You might think that this is a indication that this particular u that you chose was not a good one, and you might want to go back and choose a different u. In some problems, that might be true. But this is not one of those instances. And why? Well, notice that what we have left here is x to the fourth. If I go back to my first substitution here, u is 1 plus x squared, I can go in here and say, hey, let me look at this a little differently, from a different perspective. Let me write this as 1 plus x squared equals u. And then solve for x squared. That's u minus 1. Hey, x squared is u minus 1. So if I square this entire equation, I get x to the fourth is u minus 1 squared. Again, you might be thinking, I didn't know you could do that. And again, that's the point of watching this video and me making it. So I now can take x to the fourth, which is literally u minus 1 squared, and substitute that in here. So 1/2 u minus 1 squared, square root of u, du. And voila, you have taken the original integral written only in terms of x and written it now only in terms of u. So you are making progress in your integration by parts, in the u substitution technique. The next step is, to see if what you obtain, the integral you obtain, is actually one you can do, right? That's the whole point of the technique, to try to take an integral you didn't know how to do and convert it to one that you do. So, in this form, it's not quite clear that we know how to do that. So the first thing I'm going to do is simplify the integrand. I'm going to square this out. So this is u squared minus 2u plus 1 times square root of u du. And the next thing I'm going to do is I'm going to multiply the square root of u. I'll do that, before I do that, I'll express it as u to the 1/2. Okay, so u to the 1/2 times u squared gives me a u to the 2.5, which is u to the 5/2. U times u to the 1/2 gives me u to the 3/2, so that's u to the 3/2, and then plus u to the 1/2. Okay, all that du. And at this point now, this is an integral we know how to do. Each one of these terms is a power function, so we can apply the integral version of the power rule. And because we know about the properties of integration, right? Check out video 18.2, I believe, in this series for a review of that. We know that we can split up this integral into the integral of 1/2 u to the 5/2 minus, du, minus 1/2 times the integral of 2u to the 3/2 du plus 1/2 the integral of u to the 1/2 du. So that's by properties of integration. And then I can apply the integral version of the power rule here. So let me eliminate some of the clutter and bring things up so we can do some of that work. I'll have to, oh great, it did not erase my u here. All right, so then let's bring all this, see if I can grab the whole thing. There we go, bring it up there. And then now we do each one of these integrals. So I'm going to add 1, 5/2 plus 1 is 5/2 plus 2/2. 5/2 turns into 7/2, divided by the result. Minus 1/2 times 2 u to the 3/2 plus 1, that's 5/2, divided by 5/2, plus 1/2 u to the 1/2 plus 1, that's 3/2, divided by the result. Okay, plus c. All right, so this is, not the nicest looking version of all of this. So let me just make it look a little nicer. Dividing by 7/2, same as multiplying by 2/7. Divided by 5/2, same as multiplying by 2/5. So I get a 4/5 here. And then divided by 3/2, same as multiplying by 2/3, u to the 3/2 plus c. And then we have a bunch of 2's everywhere, right? So these 2's go away, those 2's go away, and then this 2 leaves you with the 2 up there. So I get u to the 7/2 over 7 minus 2u to the 5/2 over 5. Great. Plus u to the 3/2 over 3 plus c. Okay. So this is where we have gotten to. And then what is the last step, right? Are we done? And the answer is not quite, because as I usually say, right, we started with an integral in terms of x. We are attempting to give an answer not involving x's, so there's something off there. And what's off is that I need to go back to x's. So everywhere you see a u, you put in a 1 plus x squared in there. And then, so that's the last step in this problem. 1 plus x squared. to the 7/2 divided by 7 minus 2, 1 plus x squared. So I'm just substituting everywhere I see a u, I substitute the quantity 1 plus x squared. Great. 3 plus c. And this now really is something that we can claim to be the final answer. As I always say, you can check your work, one of the nice things about integration, by differentiating your answer and ensuring that what you obtain is the integrand, right? This thing up here, the integrand. And this is, a lot of, this one in particular will take a little while to differentiate, a lot of chain rules and simplify, but you should check, good little exercise just to review your chain rule and just differentiation in general, that indeed differentiating that gives you that. Okay, the major takeaway from this video that I would like you to remember is that intermediate step where we had chosen u to be x squared plus 1. We had converted this integral into x to the 5th square root of u dx, and du was 2x dx. The two things that we did that really enabled us to make this work out at the end was, number one, right? Remember we said x to the 4th times square root of u du times 1/2. We, in other words, siphoned off an x from x to the 5th and substituted x dx for 1/2 du. And then the second thing we did was, so in other words, we used that first step, we used du, to help us get rid of one of these powers of x. Then the second thing we did was we went back and we used the other part of our u substitution, this one, and we expressed x squared as u minus 1, and then squared that to get rid of the other powers of x. And that's what enabled us to then say, okay, this is u minus 1 squared root of u du, therefore all in terms of u's. That's the first step of u substitution. Okay, if things were more complicated, let's say this was, I don't know, x to the, let's see, trying to make something up here. What if this was x to the 4th, right? X to the 4th. What would have happened? Well, one of the powers of x would have been siphoned off by this step, right? So that would have dropped it down to x to the 3rd. Okay, but then now I would not have been able to, like I did over here, square x to get x to the 4th because I just need x cubed. So what would I have done? Well, I would have gotten here and said, oh, well, x squared is u minus 1. I need an x cubed, so I'm going to raise everything to the 3/2, right? Raise everything to the 3/2 instead of squaring it. That would have given me x cubed is u minus 1 to the 3/2. Okay, and then at least that gets me over here to the point where I can now, again, rewrite everything in the integrand in terms of u's. And this would now yield a more complicated integral to do. But, the point of this ending of the video was to show you that it is possible to treat this, substitution, u equals x squared plus 1, or whatever u substitution is. It is possible to use algebra, right, to manipulate it in so many different ways to get you expressions for x that then help you reduce your integrand down to only u's. Okay, so keep an open mind about all the different ways that you might be able to do that. And I encourage you to go back through this video and to study how we did that initially in this example, and then what I just talked about here and how I got u minus 1 to the 3/2 here. Again, this is probably, I would say at this point, the advanced type of u substitution where you're having to manipulate the du equation and you're also having to manipulate the u equation in your attempt to convert the x integral into a u integral. Okay, thanks for watching.